Hello, good morning, good afternoon, everybody. Hopefully you can hear me okay. So thank you for joining our web meeting this afternoon or this morning, depending where you are in the world. Welcome to our virtual event, Fundamentals of Design Space Exploration. So my name is Justin Whitford, and I'm from Mayor here in the UK, but the majority of the presentation will be given by my colleague, Adam Martin, and our colleagues from HIETA. So next slide, please, Adam. So this we're going to go through today. We've got 5 sections. We're going to crack through these fairly quickly. I'm sure there's going to be a number of questions. So we'd like you to ask any questions in the question panel within the web meeting session. And at the end of the session, we will go through as many of those questions as possible. And obviously, we'll follow up with anybody who didn't get their question answered. And I apologize for that, but we'll do what we can. Thank you. So next slide. So just a little about Mayor. Many of you will have heard of us. We've been a software and services organization for over 30 years now, working very closely with Siemens to provide a number of services and software and co-authoring of simulation tools within the SimCenter, NX and TeamCenter environments. We're a high technology company, over 200 employees, and we are very much within the digital manufacturing and simulation and virtual prototyping and virtual commissioning area. We've got a long pedigree of working with high-end clients to provide quality services and software and adoption within the industry. Next slide. So we're very proud that in 2019, we were the #1 global partner for Siemens Digital Industry Software. For both software development and support and resales of the technology to a number of clients on a global basis. So this event is actually being broadcast from Mayor in the UK, but we're very much a global organization. I know there's a number of people from different countries on this session today. So just one last slide, and then I'll pass over to my colleague, Adam. So to give you a little bit of background about the kind of capabilities and technology we provide, we're all about taking CA simulation, physical testing, system simulation, and taking all of those technologies within a number of different software products and tools to provide really great capabilities for our clients. Today, we're going to be looking more about the design exploration, design optimization side of things, which is really a kind of a wrap over of a number of those different technologies to provide an integrated platform to allow you to really get into and to get the best possible performing products out of your organization. So with that, I'd like to pass over to Adam Martin. And once again, please do ask questions in the questions panel, and we'll do our best to answer all of those at the end.
Thank you very much, Justin. So good morning, good afternoon to the folks on the line. So I'm going to sort of be the main presenter for this session, and as you saw from the agenda in the middle, we'll talk with Recep from HIETA, and he'll share some of that story. But just by way of quick introduction, so I'm based in the UK. I've sort of got 20 years of accumulated experience in simulation and particularly design exploration. Also, a few other interesting things. Obviously, we can't meet, but just a little background on what some of my interests. My very first engineering project was to design a dustbin door for a train, and things have thankfully progressed from there, but it was a good start. As you can see, I've got a kind of quite an interest in being outdoors and building stuff in my own time. So as Justin introduced, for the agenda today, we're going to take you through some of the sort of fundamentals of design exploration, some of the whys and what you do, and then we'll hear from HIETA and a little bit of their interesting story around additive manufacturing and also how they're using design exploration as part of their business, and then some other customer examples which I think will be of interest to folks listening. and then we'll finish off with sort of some ideas for next steps if some of this is of interest to you. So thinking about design space exploration, these type of questions that you see on the screen right now are kind of common for most of us in our day-to-day different industries. So if you're working in aerospace, for example, you have always a challenge of maybe maximizing lift and minimizing drag, but figuring out what configuration of a wing, twist and taper might give you that. You might be in life sciences, looking at the design of a syringe to be efficient for what it needs to do, the shape of that, the draw rates and the sizes. You might be in the marine industry and looking at how to get a fuel efficient design for the shape of your boat or propellers. So these are all kind of common things, and this is really where design exploration comes in. So we can simulate these things, and then how do we improve those designs and use design exploration to answer some of these questions. So being quite practical, I always like to start with a real example of these things and help folks understand what we're talking about when we're doing when we talk about design exploration. So on the screen at the moment is a relatively simple engineering example, but shows some of the will help us or hopefully help me to demonstrate to you and show you some of the key aspects of design space exploration. In particular with a product called Heat, which allows you to bring together different simulation tools and explore design spaces to hopefully improve your products and understand them better. So as you can see in this simple example, we're going to be looking at how you might maximize the efficiency of a heat sink. So something we're all pretty familiar with, the kind of thing you might find on any circuit board. But at the same time, look at the cost aspect of that and how can we minimize the cost but get the performance we need in the design. So we're going to be looking at kind of automating a process which is going to update our geometry, run a simulation and calculate the manufacturing costs, and then compare designs between the cost of the design and the performance of the design, in this case the kind of operating temperature or maximum temperature of the heat sink. So in order to do this, I'll sort of take you through 5 critical steps or pieces of design exploration, explain some of the theory and practice behind that as we go through the next few slides. And to do that, I've put together some video demonstrations which take you through some of the highlights. But before we get into the actual doing, with any design space exploration, one of our key recommendations is you always start with a clear problem statement. So you look at what your objective is for design, and this is kind of classic engineering. And in this case, we want to maximize the cooling efficiency and minimize the cost. We might have some real constraints in the challenge. So here we've got a kind of maximum operating temperature above which the chip will maybe fail or have reduced life. And we have a mass constraint. You could imagine if you were doing this with maybe some kind of aerospace packaging, you might have a very stringent mass constraint. If it's a mass produced thing, that might not be so important, but the cost would be a bigger factor. So there's some aspect of trade-off here. And then we also have a design space, which is defined by basically the variables in our design that we can change. So when we talk about design exploration, that's what we're doing. We're trying different designs within a design space. And here for this case, for this example, we've got 7 or 8 variables that we can change. And we want to see how those affect both the cooling efficiency and the cost of making this heat sink. So we've got a set of simulations which will do that. So the next question is, how do we couple those together and build out a process which will allow us to evaluate different designs? So in this video, we're going to be looking at how Heat, which is one of the tools in the SimCenter portfolio, will allow us to couple together the NX CAD geometry, which we saw earlier. It will also work with other geometries. You're not restricted to just NX. So we have examples of, say, SolidWorks and other CAD tools that are out on the market. Also the same, we're going to use Star CCM in this case for the CFD analysis, but that can be anything to do the CFD work. And then we'll use Excel. Excel is, in my experience, is still used heavily in engineering, and we'll just show how you can bring that into the process and bring knowledge and know-how in from Excel sheets. So just skipping on there. So this should run through a video. So the first step we're going to do is automate the geometry generation. And you can see we've got a model in this case from NX, which is parameterized, and we can change the things like fins and dimensions. So we're now in the HEEDS software, and we're just going to set up our heatsink design process. And you can see there's different portals available to connect to different tools. There's lots of them, but we're interested in the NX portal. And here we've picked it, and we just pointed it at our part file, which has got our heatsink and design in, and it has read all the different expressions. So these are the things that we can change in the design, and we've selected which ones we want to change, and then configured the portal to update and save a new design. The next step for us is to bring in our analysis, in this case from Star. So here we're using the Star portal. You can see that we're starting to kind of have some kind of execution order in our process. And we're adding in the simulation files and also configuring it to pick up the geometry that we've updated from NX in our Star analysis. And we're interested in the temperature of our heatsink. So we're just showing HEEDS how to get that temperature back. You'll notice there's kind of no coding involved in any of this. It's point and click, drag and drop to configure and push data in and out of NX and Star. And finally, we'll look at adding in Excel to our workflow. So again, we drag and drop in the Excel portal. And in this case, we're using named cells, but you can also pick cells directly, which you'll see shortly in the video, from the Excel spreadsheet. So here we've got a view of what's in that spreadsheet, and the variables that we're using as inputs, and calculating a cost. So we've now kind of connected our process up. Another thought is we might want to run the Star analysis, for example, on different remote machines, or on a cluster, or even on the cloud. So this is another thing we can set up through the HEEDS tool. And here we can maybe pick a cluster to use, and you can see it's indicating here that that's the case. And then once we've done that, we can potentially run maybe more than one analysis at a time. And in this situation, maybe we choose to run 4 analyses in parallel. Another thing you can do is you can run different codes in parallel. It makes not so much sense in this particular example, but in other examples, maybe where you're doing the maybe looking at the CFD and structural responses, you could run those in parallel. So this takes you through very quickly kind of one of the foundations of design space exploration, and that's kind of creating a process and automating that with your different simulation models. So with that in mind, just to kind of get a bit of interaction going, we've set up a poll just to see kind of what people typically have in their so if I press launch, I will hope that you're seeing a poll page which is asking the question about the number of simulation tools that you typically use in your design process. And we can collecting some data. I can see some folks answering. So I'll give you a few seconds. But yeah, as you can see in this particular example, we're able to couple together different simulation tools. Particularly when you've got more than one tool, this type of approach becomes very powerful and takes out some of the major manual steps in between passing maybe geometry to your simulation tools, and you can automate those kind of non-value add steps. So I'll give you a few more seconds and then I'll close the poll and we'll get, hopefully you guys will see that what's, so just closing it now. And if I hit share, so I assume people are seeing on their screen the poll results. So it's quite interesting. A majority of people are using more than 2 to 3 simulation tools. So the type of process we've just looked at would be something you could do that with the HEATS tool to build up one of the foundations of your design exploration. So let's go back to sharing my screen. Okay, so I'm hoping you can see my screen again. So back into building up our design exploration. So the next stage is we've got a process that we've automated and maybe we're able to distribute that to different compute resources. And then what we want to do now is start running some designs and searching the design space that we talked about earlier. So one kind of classical approach to that might be to start with a DOE or variable screening and work through the process in that way. With the HEATS tool, what we typically recommend customers to do is actually start with an algorithm called Sherpa. This algorithm is a optimization, ultimately an optimization algorithm. But the way it works is it combines together a number of different algorithms, and so it kind of becomes a hybrid of those. And rather than kind of tuning the algorithm, you give it a time or a number of iterations that you're prepared to spend exploring the design space. And then the Sherpa algorithm kind of takes over from there and looks at the design space as it explores it and adapts. So this way, you don't have to do some of the kind of what's traditionally been hard work of doing variable screening and DOE. You can still do those things, as you'll see with HEATS. Those options are still open, but you know this is quite a good way of starting and start getting towards some of the goals that you've set quite quickly. So let's have a look at how you would do that with our heat exchange example. So if I click here on that. So again, a short video just running us through setting up what we call a study in HEATS. So as I mentioned, you can also do DOEs, and you'll notice on the list there that you can also run robust and reliability things. So this is where you have variability in your variables. But the classic one, and the one we recommend most people to start with, is a parameter optimization using the Sherpa algorithm. You would have seen there's other algorithms available. And then the next step of setting up your study is that you define the variables. So we didn't really cover this much during the process capture piece, but here we have a number of variables with maximum minimum limits of what we're going to change. And the last variable there was a material, which is a discrete variable, which we're also changing in this study as well. Here on this page, we're looking at setting up our responses. So we're interested in the maximum temperature of the chip and the minimizing the total cost of the chip. So we want to bring that temperature down, the maximum temperature down, and the cost down. We also had some constraints, if you remember, on mass and chip temperature. It could not be above 85. So the next step, we've configured our study and we set it running. So this is an example of that study running. About 2 or 3 minutes in, and this is just running on a reasonable laptop. The analysis times are not long on this, a few minutes for the simulation. We start getting some feedback as it runs, and through here we're just seeing in-run data coming back from the first couple of feasible designs. Feasible versus infeasible. Feasible are designs which meet our constraints that we defined in our setup. And after around about six and a half hours here, you can see the timings. We've run through 500 designs, and we've got about we've got 375 feasible designs. And in this view, you're seeing what we call a parallel plot, and a number of those designs are shown on that plot. And the other thing that you see is the red lines mean that those are basically infeasible designs versus the blue lines, which are feasible designs. And you'll also notice we've been automatically extracting some nice views from the analysis run in STAR in this case, so you can see the shape of the heat sinks. So that's how we would set up the run and run this. And so now the next ingredient to our design exploration is to kind of interrogate the results and figure out if there's some designs in there of interest. So again, a short video continuing on with the heat exchanger example, heatsink example. So here we've plotted, I'm just going to pause it there, we've plotted each of those 500 runs, or actually each of the feasible runs, so about 380 runs on the plot, with cost versus the temperature of the heatsink. And remember, our original goal was to minimize the cost and minimize the maximum temperature of the heatsink. So we end up with a set of points, and you see there's a kind of curve here where the designs are pushing either they're cheaper or they perform better. And this is typically known as a Pareto front. So you see that we draw that on. And so there's a bunch of designs on there which we can use heats to extract into a kind of simpler view. And these are our trade-off between cost and performance. So if we look at this view, you'll notice the colors also link to mass, because that's an interesting factor here as well. So we've got expensive but efficient designs at the top, reasonable cost designs in the middle, and down at the bottom at the higher operating temperatures near our constraint are lower cost designs. So then it's down to an engineering decision maybe to choose which heatsink to use. Another view to quickly show you is, this is more like a tabular or Excel type view of all the designs, and HEADS ranks them, and this is the top ranked design. This is maybe the coolest feasible design, i.e. the lowest operating temperature. So we can quickly go through and find different designs which meet different criteria. What might be influencing these different designs? With this influence plot, Bruta influence plot helps show that. So here the red represents cost, the influence on cost of each of the variables along the bottom, and the blue is the influence on temperature. And we can see interesting things like, obviously, the length influences the cost, and it influences the temperature. And finally, in this demo, you can combine these different outputs and reports and kind of cross-check things. So here we've got the design table along with a parallel plot and what we call a self-organizing map, which is just a way of grouping common designs together. And if I pick an item in one of these views, it's highlighted in all the other views. And I can also, from the self-organizing map, see a family of good designs. So this happens to be one of our top ranked designs. You can see it's rank 1, and there's a whole group of similar designs. And if you look at the black line here briefly, you can see that most of those top ranked designs are full height, very short, so lightweight, and low material, therefore low cost. And we can see the common pattern, and they're all made of aluminium rather than more expensive copper material. So it's a quick tour of what you can do with, within HEADS for design exploration, and kind of also a classic way that you would approach any design exploration project process in this way. So just before we go to Richip and hear a little bit more about what HITA have been doing in this space, some kind of key takeaways and pointers for success based on our experience of doing these kind of things with many customers. So as I said at the beginning, it's always great to start one of these processes with clear objectives and a well-formulated problem. Of course, that goes for any engineering project you do. The other thing is validated and fit for purpose CAE CAD models. I said fit for purpose because we can do this for detailed design, but we can also do this for sort of system level design where we might not need so much fidelity in the models and quicker running models, but still have value to do design exploration. So having the appropriate level of model and something available. And this is one of my recommendations. Always start with a simple process and then build up and adapt. You know, it's the 80-20 rule. Often you'll find with that first simple process, you'll start getting good results and a good step forward, and then you can add more detail. The other great thing about these type of approaches is you can look at how you can maximize your current software assets and compute resource. So if you've got licenses, you know, that are not being used at weekends, something like this can go away, do a design study over the weekend, and also take account of any clusters or cloud compute resource you've got. So it can be very efficient for that on that side of things. And another thing that I also quite like about this whole space is you can try things. There is incorrect answers, yes, but what you are looking here is improving designs and trying things to search and discover better designs. So the approach is and one of the key things with something like HEEDS is you can build on past experience. You can use past results and add to them, so you can have an additive approach and learn as you go along, and there's always better solutions to discover. So with that, we're gonna sort of change, and I'm gonna ask Recep from Hyeta to introduce himself. He's got some interesting stuff to share with you about additive manufacturing in general and Hyeta's story, and then he'll take you through a little bit of some of the stuff that Hyeta have been doing in this space, and some examples of some of the design exploration they've doing. So Recep, hopefully you're online and you can hear me. And
yep. Can you hear me?
I can, yes.
Hello.
So cool. Are you okay to introduce yourself?
Yeah. Hi everyone. I have chose some picture from 3 times built to go to see Grand Canyon here, which is impossible right now. But my name is Recep Kahraman, leading in the analysis team in Hyeta Technologies, and I'm expert mainly in CFD, not mainly, but only in CFD right now. And I did this expertise in 30 years, industrial and academic, UK, combined with Germany as well. And as you can see, in several sectors. And I will go through some experience with very positive experience with Maya, Adam, Andrew, and Justin. Last couple of months, we developed through HEEDS and Star CCM, and with their help. And I will go through briefly about Hyeta, what we do in Hyeta, where we based, and how we can help you if you need heat exchangers. So basically, Hyeta is based in UK, in Bristol. So we are a company who developed AM manufactured heat exchangers, basically doing thermal management. And we established 8 years ago, probably a little bit more now, and we have approximately staff of 65 people. So yeah, we have 2 facilities now. One is in Bristol Science Park, which is basically mostly used for design engineers and some machines for innovation. And we have another production facility in Thornbury. It's basically nearby Bristol, 20 miles away. And we have currently 12 powder bed AM machines. We provide end-to-end product development for heat exchangers. Next one of them. Basically, we have quite a lot of products, but our main products are divided into basically low temperature heat exchangers, which are with aluminium, air, water, air, oil, or heat sinks, which Adam already presented similar stuff. So and the other ones is high temperature, which is above 700 degrees Celsius, which are we are doing Inconel and steel, air or air liquid modular for large applications. Next one, and here I have presenting very typical previous experience with the AM build and conventional heat exchanger, like a component volume, and so we, by improving the heat transfer surfaces and manifolding on it and packaging, we can you can see from 15 liters we can build it in same efficiency. In 4 liters, 55 is quite significant to 8 for CHP ones. For range extenders, from 51 liter to 4 liters. I think it's quite impressive how small they are, AM build ones. Yeah, like for packaging point of view, and AM parts are quite flexible as well. Next one, next slide, please, Adam. So we are involved in several markets like motorsports, including F1, aerospace. We are doing a lot of products there. Our partner Megit as well. After Megit investment, even it's accelerated right now. So we do a lot of power generation units and high automotive, and like as I said, like it's more like F1 and yeah, racing cars mainly. So, and what we do in mainly innovation and R&D. So we have internally developed 1D tool, Python code to sizing heat exchangers. We use CFD quite extensively, and FE analysis and topology optimization and other stuff. So which includes star CCM and heats, obviously, which Adam presented previously. So and in material and application side, we have plenty of different alloys, Inconel, aluminium, titanium, and Hastelloy, and some others as well. Right now is in development. We spent a lot of time to develop new materials for AM production, and so at the same time, I think we have good collaboration with Renishaw in machines, AM machines. So Renishaw provide us most of the machines, and so we start with them and still continuing with them. We have now new quad machines from them as well, and this is the part of the development as well. We are helping them to develop machines and so on. So this is like a overall AM technology progress I would like to share with you. This is the recuperator for motorsports we created back in 2013, if I'm not wrong. It's a long time ago. I wasn't there actually. This was prepared, I think, designed by Dr. Hussein and Niall in the company that time, and Javier. And you can see the machines that time, the primary walls with 0.5 millimeters, some porosity, and secondaries 0.2 millimeters. So that time we have only 200 watt laser machine, just one laser machine, and the build time of this part was 19 days. And if we go, the next one is today. Today one is exactly the same performance, same unit, but it's a 5 kilogram unit, and quite small one, using extensively CFD, and this is mainly because of the AM development as well, because we have also more powerful machines, like and then we develop a lot of more parameters. You can see that we can build now 0.3 millimeter primary walls and 0.15 millimeter secondary walls, and machines are 4 laser with 500 watt laser. So build time is 40 hours. So it's significant improvement in, I would say, 7 years. Thank you. Then, yeah, this is a typical node value chain, how we do stuff. So mainly we start with CFD analysis, and similar what Adam presented before. So for heat transfer, and usually we have a lot of iterations because we do it manually rather than use heat previously, and it takes a lot of iterations. You go to the CAD engineer prepare you the surfaces or a CAD, give it to you, you mesh it and run it in CFD, do processing, and decide whether it's good enough or not good enough. If not good enough, again repeating. It's an iterative process which takes a long time, and we have after that, if we are happy, we do 1D analysis and we finalize our heat exchanger and go to the build prep, where we slice them, prepare for the machines, and we can monitoring machines, as you can see there, live monitoring. We after that, it helps us to in processing and inspection, we can see if there is a problem where to identify the problem's place and time as well. So we have post-processing, obviously powder removal and thermal stress release. We have inspections, and then we save the data somewhere and we manage the data after. And as I said, we use extensively CFD, and I love CFD, so my background is CFD. That's why I just put here my inspiration why I start doing CFD, and it's I never regret it, and I keep enjoying it. So this was my inspiration to start CFD, and then this project with Adam and Andrew and Justin was based on CFD analysis. What was the motivation here? The basically motivation was, as I mentioned, we usually used to do iterative process to get our best heat transfer surfaces by using iterations and engineering best judgment. What we did here, and we did use heat to combine star CCM with CAD modeler. Basically, you can use any CAD modeler like SolidWorks as well, and you combine them, and then you give your cost functions, what you try to achieve. In this case, heat transfer and pressure loss was the case, and then we optimize the duct for that for different aspect ratios and Reynolds number. And it shortened, so you can see one shot of this, and you can see the similar process what Adam mentioned already to you. It was a very significant decrease of time, design time for us, which saves us a lot of days to come up with the best solution we are trying to find for specific application. And the Maya team, like Andrew and Adam, was quite helpful to build up, even though you have a real like an open source CAD model or any open source CFD model, they can produce you scripts or anything that are very helpful to provide you any help and support. In this case, that they're very quick in responding as well, so they will immediately set up the case for you that without losing time, which was the case here. So they help us to combine all the things and make it work, and we end up, you can see that from 3 days to 5 hours to get with the best heat transfer and lowest pressure drop in this case. So yeah, so working with Maya was, for me, is a very positive experience so far, and we are keep going, I think, in the future as well. So yeah, so I think we had a basic heats training, and after that they never they keep helping us at the after that as well. So I would like to thank them here personally. And yeah, so they provide us coupling SolidWorks with Star as well for manifold examples, manifold optimization as well, and yeah, heat exchanger ducts example, we work together as well. Thank you. If you have any questions at the end, I'm happy to answer. Thank you very much.
Thank you very much, Recep. It's great. So it's a little bit of how HIETA are using design exploration. So we have a few examples of how some of the other customers in Maya and in the wider Siemens world have been using the HEATS technology and design exploration to improve product designs. And so it's got a couple of kind of interesting examples that I hope will shed some more light on the topic for you. So The first one here is from Trek, and it's bicycle design. I expect many of us engineers on the line are into cycling and bikes, and that nice combination. So here that they were using heads and some different tools we'll see in a moment to try and minimize the drag and the mass of the frame of the bike, whilst keeping a kind of the stiffness characteristics. So it explores different designs. So if I just go here, you can sort of see the type of workflow, which is not dissimilar to some of the examples we've already looked at. In this case, the geometry comes from CATIA, and then running the stiffness and weight calculations with the Abacus solver technology, and STAR again to figure out the drag created by the frame. And you can see some little animations here of what was done. After running some different designs, it generated some a set of data to look at. And in this particular plot, again, we're looking at a little bit of a trade-off here. So drag and the size of the dots represents the mass, and this is the target stiffness in the middle here. You can see there's a number of designs where there's lower drag and lower mass, but around about the target stiffness. So that's a kind of another interesting application of design exploration in HEADS technology. So changing it a little bit here, this particular example, we're looking at, obviously in the automotive world, minimizing the weight of a body in white. Here we've got quite a lot of different simulations involved. So you can see this kind of spider chart with all the different facets or attributes of the vehicle design being considered in this, with the overall target of saving weight, but at, as is often in life, at the cost of something, which in this case was the actual cost of the design. So trading off those things. And one of the reasons I shared this is a little bit more in maybe looking at a single component, is looking at an entire system. And as you can see in this particular example, the customer here was using a large number of variables, 500 variables, which could be changed as part of this problem in order to try and reduce the weight, meet all the constraints. And you can see that, this took a fair while to solve, but 49 feasible designs to run, and 18% weight reduction for a 5% increase in overall cost. So this is really showing how you can explore the design space and the power of these type of tools. Another example here for this is from the aviation world. So one of the kind of classic uses of these of design exploration is in turbo machinery, balancing all the different constraints and for that design, and looking maybe at 1D gas path design, improving the aerodynamic efficiencies and so on through the different components, the fan, combustor and compressor and turbine of an engine. And in this particular example, this is Honeywell. And one of the reasons I shared this is we've been looking so far in many examples of kind of using commercial off-the-shelf codes, but you can also use HEADS with any simulation tool, in-house code that you run, and couple it up through a general portal. So that allowed, in this case, Honeywell to run some of their in-house 1D simulation codes to improve turbine efficiency. And there's in this world very small percentages. So in fact, they did a 0.5% improvement on the performance of one of their small engines, which is really quite significant in terms of possibly fuel savings and so on in this world. So a little more detail here. Again, classic kind of multi-objective problem, and an interesting quote here, which goes back to what I was talking about earlier with the HEADS Sherpa technology, where they're not so worried about the algorithms that are being applied. They just give it an amount of time and let it just explore the design space once they've created the problem, formulated the problem. So a couple of examples that I hope will be of interest to you. So as we sort of come to the end of the formal session, you might be, well, I would like to hope that you've got some more questions, and you might be wondering if this could be applicable to some of the challenges you have in your company. And just to sort of go back to sort of value, restating the value of this design exploration and this type of approach in engineering. So I think we're all fairly familiar with, the use of simulation. And classically, most people are doing this. They're using simulation to validate, troubleshoot, and predict the performance at individual points of their products. And so we've kind of all got access to this. The examples we've been showing today really take it up the next level. When we talk about automating and exploring, we're getting basically more value from our existing simulation tools, processes, and it allows us to explore, the design space as we've seen in the different examples, and that leads to innovation, improvements in the designs, new ideas, etc. So that's why we think this is important. And to get started, Recep mentioned a few of these things. So we have quite a lot of experience in helping companies get started with this journey, and then what to do. So I'm going to hand back to Justin, who's just going to talk a little bit about what we do in a typical guided evaluation for design exploration tools. Justin?
Yep. Thanks, Adam. Can you hear me okay?
Yep.
Okay, look, great. So really just want to talk a little bit about, how things move on from here. And I think the experience that Adam and myself and the Maya team have got of actually deploying HEEDS type technology is really important here. So what we've tried to do is put something together which shows a process we can go through, even from a remote perspective, from with the current times, etc. So what we'd like to offer everybody on the call today is really an opportunity to have a free one-to-one assessment as a web meeting with Maya. And what we'll do within that session is discuss a little bit about your challenges, about your software tools, try and understand what we could do for you, and really understand how applicable HEEDS will be to the particular challenge that you're looking to address. So that's, free, open to everybody. Please, talk to us about that, and you'll actually get, at the end of the presentation, a survey, and in that survey there will be an opportunity to say, yeah, please contact us and set something up. So the next stage, should we, go through that part with you, and you decide that, I want to take it to the next stage, typically we would go into an on-site activity with you, and that would be through a HEEDS online training program, where we'll work with you, quick start, typically one-to-one or one to a group of people within your company, and we'd probably spend around half a day going through a getting started course. And then really we'd try and understand what is key objectives for you and try and work out the targeted use case and benefits from a potential HEEDS design exploration, design optimization activity. And we would handle that and manage that with remote guidance from Maya and support, etc. And then obviously, if that is successful and we help you to build a business case for this kind of technology, we can discuss different licensing options, tokens, services, whatever it might be, to really ensure that the best possible configuration of license is deployed with your organization. And obviously, there is a long-term support activity that we work with our clients, as through the first 2, 3, 4, 5, 10, let's say, projects that you work through HEEDS. So again, at the end of the session, there will be a survey that pops up. In that survey, there'll be a question that will allow you to basically say, yep, please contact us, and we'll work through a one-to-one engagement with you. Okay, so at that point in time, this is really the end of the formal presentation. You can see some nice imagery here and some key messaging around HEEDS and what it can give to your organization. So at this point in time, if you've got any questions, please put them into the chat window, into the questions window, and we'll start to answer some of the questions. So let's just pick a few here, for example. I've got one question which says, what does the acronym HEEDS stand for? And I'm not going to ask you that question, Adam, because I've got the answer myself. It stands for Hierarchical Evolutionary Engineering Design System. So that's a great question. Here's one for you, maybe, Adam, to answer. Will the software still work if you cannot parameterize your CAD model?
So this is a key, good question. So yeah, you do need to be able to parameterize to use the parametric optimization capabilities we saw today. However, if you have something which you want to do shape optimization on, so we have some topology optimization tools. So it's not something we've necessarily talked about in this webinar, but if you wanted, we could definitely have tools available within the SimCenter portfolio that could potentially help you there. But again, I would recommend the asker of the question just to give us a shout, or we could spend some time and look at that. So yeah, what we've looked at, things like Sherpa work on parametric or parameters basically as inputs and respond with parameters. When we get into shape optimization, topology optimization, we have a lot of tools and a lot of capability. So that's something we can explore. There might even be a case for combining the two. So yeah, that's something we can do, but HEEDS might not necessarily be the best tool for it.
Okay, that's great. Thanks for that answer, Adam. Next question, can I use HEEDS to help correlate simulation to test results?
Yes, you can. So you noticed in the examples, or most of the examples you saw, we had a kind of target parameter, but we can also have a target which is a match to a data set. So built into HEEDS is the ability to match data curves on a plot. So we can have a measure of how well our simulation data is matching maybe test data, which is represented as a performance curve. And that is also a common use for HEEDS technology. So I didn't mention it at the time, but the Honeywell example we looked at, that's another thing that the Honeywell use HEEDS for, is to correlate measured data or test data with simulation data and tune the simulations to match in critical areas.
Thank you for that, Adam. Okay, Recep, are you on the call?
Yeah, I'm still here.
Okay, so here's some questions for you. What is the minimum scale of heat exchangers in terms of their application? Can they be used in CubeSats?
I mean, it's a very difficult question to answer. I think it depends on specs, what they're trying to do. And I mean, if they contact me, we can give them precise size for their case. But I think it's very difficult to answer this question here.
Okay,
without any numbers.
It sounds like a follow-on conversation is required and facilitate that. No problem at all.
Yeah.
Another question for Haita. Do you have any experience on ceramics, such as alumina?
We have some experience with ceramic, but not much. I think we are doing some parameter study on this, but I think we can do ceramics. Yeah, we have some experience, but not as metal.
Okay, perfect. Another one for Adam here. Can you build a surrogate model in HEEDS?
Yes, you can. We didn't show or touch on it today, but there's a whole suite of surrogate modeling techniques available with different fitting algorithms, and then you can use those surrogate models within your process as well. So you might, for example, if you've got a long running simulation, you might build, do a parameter sweep DOE, build a surrogate model, and then use that as part of maybe a system level design study. But short answer is yes, there's quite an extensive set of capability around that.
Okay, awesome. Thank you, Adam. Another one I'm going to answer myself. Can we get a copy of the presentation? Yep, you're going to get an email tomorrow, everybody, with a link to the recording. And if you have any questions, feel free to contact Mayor and we'll provide any answers required. Okay, so 2 or 3 more questions I think we've maybe got time for. One for you, Adam. Within the software, is there an area in which we perform some sort of sensitivity analysis for the optimization problem?
Yeah, I went through it quite quickly, but when you look at the web recording, you'll see the influence chart, and that gives kind of an idea of the influence and sensitivity of the responses to the different inputs of the simulation. And there is also some tools for looking at the response sensitivity. So yes, there is something. And again, follow up, let us know, and we can take you through some more detail on those capabilities.
Thank you, Adam. One quick question: can you move the slide to your contact details slide, please, Adam? And whilst you do that,
yes.
Brilliant. That was easy. Will HEEDS work with SimCenter? The variables are essentially thermal couplings, boundary conditions, non-geometric variables.
Yeah, so it will work with SimCenter. So I showed in the example earlier it working with NX, but it equally works well with SimCenter, and it's got a nice advantage that it can directly query the expressions. So that's your variables. So you can expose, say, boundary conditions, maybe a load or a pressure as part of your optimization or design exploration. Non-geometric, again, I refer back to the previous answer. It depends what it is. HIDS works is a parametric optimization tool. So if it's broadly a topology optimization that's required, then there are topology optimization tools available for which sit inside SimCenter. And again, we could, that would be a good discussion to figure out what's there and which approach might be the most suited in that particular scenario.
Okay, thank you for that, Adam. Here's another one. Is it possible to use our own non-commercial simulation codes with HEEDS? So I'm assuming that's in a situation where someone's got their own internal tools or something.
Yeah, so again, I hinted on this. So earlier I talked about the portals. So when you run HEEDS, there's a set of kind of out-of-the-box portals for things like SimCenter and SolidWorks and other tools, a wide range of simulation tools. But there's also something called a general portal. And basically, if you can run your in-house code or your non-commercial code from the command line or from some kind of API, then it's ideally from the command line, then it's pretty easy to integrate. The HEEDS also has, we saw the Excel integration with looking at the Excel spreadsheet, but it also has the ability to read and write data from sort of text-based input and output files. So again, this is a very classic use case of these type of tools. And yeah, so that is all supported. So, and again, ideal if you want to speak to us and find out a bit more, we can dig into the detail of the possibilities in that space.
Thank you so much, Adam. So look, it's the hour, so I'm going to call this to a conclusion at this point in time. I do appreciate that there are some questions that we have not answered. We will get back to the questions and come back to you with an answer directly. So I apologise for those folks that have asked but haven't got an answer at this point. So look, we'd like to thank you very much indeed for your attendance today. Thank you, Adam. Adam's contact details up on the screen, also the Mayor main website. Please contact us, and also the next webinar that might be of interest to on this call is on the 17th of June, Advantages of Optimization, working with Optisys for SimCenter 3D. So that's one of the 3D optimization tools within the portfolio. So kind of connected to HEEDS and could well be of interest to everybody. So look, appreciate your time, everybody. Let's call this to a wrap. Thank you for joining. Look forward to catching up with everybody next time. Thank you.
Bye-bye.
Bye.
Cheers, Adam. Thank you.